Okay, morning everyone. This morning I'm going to cover some more advanced GPU topics. The three I'm going to mostly talk about are profiling GPU applications, so trying to figure out where the hotspots are in a GPU application and how you might go about making them slightly colder. Optimizing data movement, so one of the things we saw yesterday in the hands-on was that data movement can be very expensive, and we've said it a couple of times. That moving data over PCIe can take a long time. It's application dependent. Some really need to optimize data movement. Some can get away without really thinking about it. It depends on how much data movement your application actually needs. And then I'm going to cover using MPI with GPUs. So what features of, or how interoperable are they? I mean, obviously you can copy to the CPU, call your MPI as normal, copy back to the GPU. But you can actually integrate them to a certain extent and use device pointers or device data directly with some MPI implementations. So I'm going to start with profiling. There are many options for profiling tools for GPUs. Some from NVIDIA, some not from NVIDIA. To go through these, nvprof is a command line profiler. It's as simple as typing nvprof / your executable name. So it's at the simplest level. So you can run that very easily. And then there's a visual profiler. So the visual profiler is standalone, nvvp. nvvp is on Linux, Mac, Windows. It's a little bit more than a visual interface into nvprof. It has timeline data as well, and will also provide you with guidance, I guess is the best word. So it will tell you what it thinks is likely to be the best thing you can do to improve your performance. Sometimes, you have to use your brain when looking at the guidance, because sometimes the guidance will say, well, optimize this kernel, but you already spent 20 hours optimizing this kernel, you know it won't go any faster. So obviously there's a bit of common sense required with the guidance, but it is usually quite useful. There's also Nsight Eclipse Edition, which is based on the Eclipse IDE. That has some debugging in it, and it also includes the visual profiler through the same interface as nvvp, and that's on Linux and Mac. Finally, there's Nsight Visual Studio Edition, so that hooks into the Visual Studio IDE. It, as a profiler, provides much of the same features as the visual profiler, but it presents it slightly differently. In some cases, some of the newer features of the profiler, so most CUDA releases or most updates to the GPU platform have updates to the profilers, and some of them make it into Visual Studio Edition but not nvvp, and some of them make it into nvvp and not Visual Studio. It's just a Windows versus not Windows thing. And there are also some third-party profiling tools. I'm not going to really say much about them. I'm not sure that's meant to say system. Maybe it is meant to say system. I've not heard of system before now. I am slightly confused by that one. Vampire Trace is very good for MPI applications. It can cover many ranks of MPI all using GPUs and give you quite a lot of detail about them. There's PAPI, and there's something called HPC Toolkit. I'm not really going to talk about the third-party tools in this talk. I'm going to talk about the NVIDIA tools. So, yeah, as I just said, we're going to focus on nvprof and nvvp. So nvprof is a NVIDIA profiler. NV is NVIDIA, prof is profiler, and it's a command line tool. nvvp is NVIDIA Visual Profiler, so NV is NVIDIA, V is Visual, P is Profiler, and that's GUI based. You should have both available on your systems. Here, I don't know if the GUI will work nicely. If you have X11 forwarding, I would hope it would.
It should work.
It should work. Okay, good. So here's the vector addition kernel I showed yesterday, GPU CUDA Fortran kernel. I should note that all the profiling tools work for OpenACC and CUDA Fortran and CUDA C, and pretty much anything that runs on the GPU they will work with. So the reason this is CUDA Fortran is just why not, I guess. So this could easily be an OpenACC application. Using it's easy, so we just run our executable as normal, but preface it with nvprof. So here is some output from nvprof. So you can see at the top we've done nvprof./vecad. So vecad's the name of the application, and it tells us nvprof is profiling process command, and then a lot of profiling information. So the profiling information is kind of split into two. It's got the what I describe as the GPU profile. So this tells us how much time everything is taking on the GPU, and the CPU profile, so which is telling us how long everything takes on the CPU. So you can see on the GPU we have our kernel vec-add GPU here, so that's our vector addition. But we also have these memory copies, host to device, device to host. Finally, we have memset. And this wasn't explicitly called by me when writing the application. I think I set some arrays equal to 0, and that then under the hood calls a memset. Some device arrays equal to 0. On the API calls, it goes through a whole bunch of things you didn't know you'd called, but are going on under the hood. So malloc, so memory alloc, memory copy, some things. So this will tell the runtime some of the attributes about your GPU, freeing memory. I guess we did know we did that, and some total memory, setup argument, configure call. So a lot of things, but on the whole, they're all quite low percentages apart from this one up here.
If you have some genuine host calls, nothing to do with GPU, can you also include that in that?
You can, yes. So that's a new feature with CUDA 7.5. So that's probably won't work with the latest OpenACC compilers because they're not supporting CUDA 7.5 yet.
So
it might do.
Third section in this article.
15.9 does. Okay. So yeah, it will work with OpenACC 15.9, but not 15.7. How it will display it, I think it would be a third. Yeah, it would be a third section. So going into these two sections in a bit more detail, in our vector addition example, what's going on? Well, mem copy H to D and D to H, as I said, are memory copies. H to D means host to device, and D to H means device to host. So one is uploads, I guess, and one is downloads. They take roughly the same amount of time to copy data to the host and data to the device. We have the average time, the minimum time, and the maximum time. It's only called twice. So host to device is only called twice. Device to host is only called once. So they are fairly similar. However, it is interesting to note that they total about 98% of the total runtime of the total GPU runtime of my application. So this is because what I'm effectively doing is I'm copying data to the GPU. I am then accessing each element I've copied only once, and then copying it back again. So I'm doing something that really doesn't map well to the GPU. I'm doing a lot of memory copies for very little work. If I was to replace that vector addition with 1 million vector additions, then suddenly the memory copies would become insignificant and the vector additions would take all the time. Assuming I didn't have to copy any more data for those 1 million extra vector additions. So this is actually really useful to know. and you can get this information very quickly. You just do nvprof /executable name. And you can very quickly see that, in this case, for example, the memory copies are taking all the time. So that's what I should fix. In other cases, you might see that a particular kernel you weren't expecting to take a lot of time is taking a lot of time. There's a target for optimization. In other cases, you might see something else unexpected. So it's essentially a first glance to see if there's anything obvious that you can fix. In this case, the obvious thing would be the memory copies. No. So it profiles anything that goes onto the GPU at any level. So it doesn't need PG. There is so you can target individual kernels, but I think you output it to a file and grep, or I mean it orders it by time percentage. So the ones you care about are going to be at the top on the whole, or going to be in the first 20 lines probably, because if they're not in the first 20 lines, they're probably under 5%. So no, you can push it to a file though and go through it. I don't think you can selectively do it. It doesn't add much overhead. It does add a little overhead, but not a lot on the whole. As I said, the PGI or OpenACC kernels work. The PGI naming convention is to name them after the subroutine name and then the line number. So in this case, I did do a little OpenACC version of this code, and it was called vecad17 GPU. And so the subroutine was vecad. It was line 17 of the source file, and underscore GPU obviously means it's compiled for the GPU. We probably wouldn't see if it wasn't, but that's the name of the kernel that it calls. So it's quite useful to know that 17 actually represents the line 17. It's something I didn't know initially when profiling OpenACC.
I just tried it on the example 2 we did yesterday, and there's also another one, underscore red.
So that would be reduction. So that would be your sum reduction. So the bottom half of the profile is I say the runtime measured from the CPU perspective. So this is the GPU calls measured from the CPU perspective, or the GPU API calls as well. It doesn't measure the CPU code directly. So what can we see here? Well, we've rather unexpectedly got a CUDA malloc taking 95% of our CPU time, which is 321 milliseconds one of them is taking. Now if we look at our memory copies from the previous one, they're taking 2 milliseconds. So that's a bit of a shock. And what's going on here is a similar thing to some of you may have seen yesterday, where the first CUDA API call will initialize the CUDA context. And that initialization takes some time. So what we have here is we have one CUDA malloc taking about 321 milliseconds, and you can see that the average, however, is 107 milliseconds, and there's 3. So the other 2 are taking, microseconds, probably. However, it's useful to know that initialization is going on. There's a few other ways you can initialize and isolate that time a bit. And in a large application, if your application is taking minutes, then that initialization cost won't show up very significantly. It's only because this application is taking a second or less. Again, we see those mem copies again. So this is from the host perspective. So they generally take a little bit longer on the host because the host has to set them up, then do the copy, and then do a bit of deconstruction, but not much deconstruction. So the copy from the host perspective takes a bit longer than the copy from the GPU's perspective. So the average here is about 3 milliseconds. The average up here is, well, for that it's 1.9, for that it's 1.6. So there's the overhead on the host for mem copies. They will show up as a low amount of time on the host. So there'll be the overhead from calling it, which will the CPU will work on, and then it will return instantly, so it will be a lower overhead on the host. One of the reasons it's high here is because I'm not using page-locked host memory, and we're going to go into why page-locked host memory is a good thing in the later slides, but asynchronous copies should show up a lot lower on here. And it will show up as CUDA mem copy async instead of CUDA mem copy. So as I said, there's also a bunch of other calls, most of which are done by the system, and they will also, once you're running a very long application, several of them will become even less significant. So there's a few artifacts from running a malloc copy kernel, copy deallocate kernel, because it's just so short. So that's the basic information you get from nvprof. Just what percentage of time are things using, and that's, as I said, very useful information in some cases. If things aren't as you expect, then it gives you avenues to explore. There are also a lot more advanced features of nvprof. So obviously nvprof-h is the help, and there are quite a few options. I've picked out some useful ones. These aren't necessarily all the useful ones. They're just what I consider to be the more useful ones. So here we have -o, which creates an output file which can be imported into the visual profiler. So if you're working on a remote machine and you don't have the ability to run the visual profiler remotely onto that machine, you can create a profile. You can email it to someone else if you really want to. So you can import that into the visual profiler and then use all the visual profiler's features on it. There are two types of GPU. Well, actually, let's explain the difference between events and metrics. So -m and -e collect metrics or events, respectively. Events are based on GPU counters. So there's counters built onto the GPU which count specific things going on. So they might count cache lines read or operations, operations of a particular type executed. So that's quite a low level output, and in general not that useful unless you really know which event corresponds to which. Metrics are derived from events. So metrics will take several events, do some sums, and give you a more useful, usually, number. So an example of a metric may be the read throughput from your global memory. It may be the total floating point operations you're doing in single precision. It may be your L2 cache hit rate. So that sort of thing. And you can't calculate the L2 cache hit rate from just a counter. It is based on a number of events. So the metrics are based off the events and are generally more useful. There's analysis metrics. So this is great if you're pushing something to nvvp. If you're going to then later analyze it in the visual profiler, this will collect all the metrics that visual profiler needs to do its low-level analysis. And finally, there's query metrics and query events. So that allows you to look through which events and metrics are available. There are a lot of them, especially events, and see which one you might want to use. So, if you suspect, you can get to quite low level here. If you suspect, for example, the L2 cache rate, L2 hit rate, let's say you have two versions of a kernel. One's going fast, one's going slow, and you suspect that the L2 hit rate is a thing. You can then compare the L2 hit rate between the two and see if your suspicions are correct. And maybe that can help you design a better algorithm. Maybe it can't. But that's the sort of thing you would then use. And so query metrics will give you a list of the information that is available to you via the metric system. So this gets into quite low level. We can really dig down to find out what is going on in an individual kernel. And on the whole, unless we have kernels which are showing up as 10% plus on our previous profile, this is quite a lot of work to optimize. But if you have something that is a significant user of your time, it can be worthwhile to look into this information. And maybe that can guide future code changes which will bring about faster code. So I did just speak about events and metrics a little bit more detail. Here are 4 that I find myself using quite frequently. Metrics. There are maybe 30 or 40 total metrics. But these are 4 I find myself using quite frequently. So there's the DRAM read throughput and the DRAM write throughput. So this is so these are useful because often GPU performance is bound by one of 2 things. It is bound by floating point throughput, or it is bound by memory throughput. You can find out the theoretical peak floating point throughput, the theoretical peak memory throughput, and if you then compare DRAM read throughput plus DRAM write throughput to the theoretical peak, you can see how close to peak you are, therefore how much room for improvement there is. Similarly with the floating point operations, single precision and double precision, you can see how close to the ideal you are, or you can compare yourself to QBLAS, for example. So QBLAS does efficient matrix-matrix multiplications. You can compare yourself to that, and if you're doing roughly as many floating point operations per second as QBLAS, you're doing a pretty good job. So I find those 4 quite useful, but I find I also use most of the metrics here and there, mostly via nvvp though. I tend not to dig too deeply using nvprof because its interface is command line. There's a lot of text and a lot of typing to get what you want. So an example of the metrics, I ran my vec add program with those 4 metrics. And here was my output. So you can see we have, so this is what the output actually looks like. On the next slide I have the key parts of it made a bit bigger, so you can see them. What I got was a DRAM read throughput of 136 gigabytes a second, a DRAM write throughput of 70 gigabytes a second, and I'm doing 1 million floating point operations in single precision and 0 in double precision. The problem was an addition of 1 million element single precision vectors, so 1 million element single precision vectors. So I'm quite pleased that it's telling me I've done 1 million floating point additions. If it was telling me something else, I would start to question whether I'd written my program correctly. And actually, when I was doing this, I found that I did not write my program correctly. So what I had forgotten was I was too used to working in C, so my bounds check, it didn't have this equals. So it was cutting out one of my floating point operations. So when I was here, this was 99999 floating point operations. I went, that's not right. I'm meant to be doing 1 million. So I managed to fix a bug through this. Perhaps I should have had better checking in the application. Using the time we saw before as the output of the visual profile, the nvprof, we can see we can calculate the floating point operations per second of this kernel, and works out as about 50 gigaflops. The K40 I'm running on goes up to about 5 teraflops, so 5,000 gigaflops, so about 1% of peak flops. Okay, that's not great. If I was expecting to be bound by flops, I would not be very happy about how this kernel was operating. However, I'm not expecting it to be bound by flops. I'm expecting it to be bound by the bandwidth to memory. And we can sum read and write and get about 206 gigabytes per second. Peak for this machine I know is 288. I know that I have ECC on. I know that I can do a memory copy and so a device-to-device memory copy, copying memory from device memory to device memory. And I know that peak, so just because I've measured it, is also about 210, 220. So that's the theoretical peak is 288. Achievable is probably 210, 220. So I'm getting 206. I'm fairly happy about that. That's 72% peak bandwidth. If you get 72% peak bandwidth, you're probably memory bound, and you should look at either reducing the number of memory operations you're doing or doing them in a more efficient way. Now, I'm just doing a vector addition. It's hard to do it in a more efficient way, so I'm fairly happy with this. There may be a few percent I can find, but I'm not going to get a 2 times speed up. It's impossible for me to get 2 times speed up because there's no memory I'm moving. I don't need to move. So that's useful. I mean, that's not taking me long to get. It was just a single command line there. It's quite a long command line, but it was just a single command line. Doing a few sums based on that, I can see that I am memory bound, and I'm probably not going to get much better. Now I'm going to move on to the visual profiler. So that was all the command line profiler. It's available on your machines, and I think part of the third hands-on will be using the command line profiler. Now I'm going to talk about the visual profiler. So there's 2 ways of importing information into the visual profiler. You can either run your executable through the visual profiler. It supports local and remote connections. Or you can output it from nvprof and then import it into the visual profiler, which is useful if you don't want to look at it now, you want to look at it later, or you want to email it to a friend, or you can't hook nvvp into your environment. So say you're working on a remote system, it can be awkward to get nvvp working. So, there's a couple of ways of importing it, and this is what you get after you have imported it. So I have 2 timelines here. I have the timeline on the top, which is my total application timeline. So we can see here we have a number of things I'd like to point out. Firstly, tells us we're running the vec-add process. It's useful. Gives us a thread ID. That's probably not very useful. It then tells us what that thread is doing. So this is a CPU thread. And if you remember, we had this CUDA malloc, which was taking a very long time, and this is the context initialization. So that starts here and ends all the way over here. And if you look really closely, you can see there are some lines here, and this is where actually all the work we wanted to be doing is. So this is the GPU we're running on, the context in the GPU, the memory copies, and then the computational regions. So you can see we have memory copies and computational regions all the way over here. Now, if I had a much longer kernel, I'll show you a much longer application. This initialization time is not that significant. It's 0.8 seconds. So if you're running for minutes, then it looks quite different. I've then zoomed in the visual profiler to show just that last little bit, and you can see we have actually this is what a millisecond increments on the axis here, and we can see we have our memory sets here. We have our copy 1, copy 2, synchronous. It labels them as synchronous. Then we have our vector addition, and then our copy back. So as expected, our copies are taking a long time. The gap here between these 2 copies, I haven't really worked out why that's there. I suspect it's to do with the memory being pageable, and that causing a large overhead. But for this particular application, I haven't figured it out. Usually, I don't see that on long applications, so I'm not entirely sure why that's the case. But the one thing you can clearly see, though, is that our vector addition is really insignificant compared to our copies, which is what we expected from looking at nvprof. This does give us a nice sort of view of it, though. We can see you can see what 1% looks like in real life, and you can see a number of other different things with the timeline. So here is another application, a much larger application I ran to nvprof. So this is Nemo, ocean modeling application. I've run, what is this? I think it's 24 time steps of Nemo, so less than you'd run, I think, in practice, but enough to show an interesting profile. So when I created this timeline, I wasn't interested in the entire application. I was interested in roughly which bits are doing expensive things and which bits are not. You'll notice I've got the, this is OpenACC, so I have the OpenACC namings. So that's lim_RHG_449_GPU. So that tells me the line number and it's subroutine? I think it's subroutine. Line number and subroutine that's running in. So in this case, the initialization all goes on right at the left edge here. This area is the program initialization, so there's a lot of reading data from memory, a lot of copying to the device, and here is the actual working section all the way through this part. You can see that you can quite visually see the time steps. So this particular function, subroutine is called once every 3 time steps, so you can see 1, 2, 3, 1, 2, 3, 1, 2, 3, etc. So you can see the shape of your application. You can really visualize what's going on. You also have these percentages ordered by magnitude. Nemo is quite a flat profile, so the most significant kernel I had in this particular run, I can't remember which run this was. It was a final optimized run, or it was just a test run to try out something new that I'd implemented. But you can see that of the GPU time, lim_RHG 449 takes about 5%. There's quite a lot of information there. I'm now going to zoom in on this profile. So obviously you...
Can I just ask a question? What is device-to-device copy?
So that is when your memory starts on the device and your memory ends on the device. So if you want to duplicate an array, for example, you don't want to have to go to the host and back. It's the same reason you do a memory copy on the CPU, if host-to-host memory copy. So this is the entire program, but we only have so many pixels on our screen, so it's quite hard to actually represent what is going on at the low level with such a large overview. Fortunately, nvvp allows us to zoom in quite far. So these are increments at the top here of 1/4 of a millisecond, so 250 microseconds now. And this is one of the parts of Nemo that didn't do so well. So this is the PCG solver in Nemo. Now, you can see that here, we're not on the GPU as much as we want to be. And this is one of the messages I take from this, looking at this. I can see that we have these kernels, and they run all right. And for example, in this section, it's looking all right. We're permanently on the GPU. But around here, we have a lot of time spent in this inner loop. So this is one PCG iteration, and here's another one. So we're looking at a whole iteration from here to here. You can see that we're not on the GPU as much as we'd like to be. And this, again, is really quite useful to know, because it means that there's most certainly room for improvement. If all those white spaces, those blank spaces in the compute line could be removed, then suddenly our PCG solver would be going, 2-3 times faster? That's clearly quite nice to be able to get hold of. So by knowing that there are these white spaces, I can then try and come up with a strategy to remove them. In this case, the reason there are white spaces is because it takes about, somewhere between 5 and 20 microseconds to launch a kernel to the GPU. So that is CPU time taken to launch a kernel to the GPU. So if your kernel does very little work, and in this case, a lot of the kernels were doing very little work, that overhead completely dominates the time. So you can just about see it up here. We have these large blocks are the launching commands, and that's what they're actually launching. So it's blocked by the overhead of launching things. And the problem here is actually not enough parallelism. I don't have enough work to do on the GPU. A number of ways around this. You can fuse kernels together. So if you can fuse kernels together, you have to pay half the launch overhead, or you can have more parallelism. You could also overlap other operations with this PCG step. So if I had an independent set of kernels, I could be running them at the same time, and then we can overlap the overhead with the kernel execution. So nvvp allows you to really zoom in, see the details at the 250 microsecond level, even more. Like I could zoom in and have this fill the entire screen. So it does profile at the really quite fine level with these timings. I think it's microsecond accurate. It might be lower than microsecond. It's really quite precise. And using that information, you can make your application faster, potentially. So going back to our vector addition, we looked at nvprof and how to get some metrics out of nvprof. We can do a similar thing using the application analysis feature of nvvp, or the visual profiler. Alternatively, we can have imported something collected with analysis metrics, and then we can get more information about the kernels. So I'm going to go through examining individual kernels here. So this is a menu you'll see in the bottom left-hand corner if you open up a timeline in the visual profiler. It's quite clear to see. But will show me a screen like this. So in this case, it's telling me that my VECAD GPU is the most significant GPU kernel. It doesn't include the memory copies. It's the most significant GPU kernel I have. And I also have these memset kernels, which I didn't write and are less significant. So I want to analyze that, so I click on Perform Kernel Analysis. And this is what it tells me. This says for device Tesla K40M, so K40 is similar to the one you're running on, the kernel's compute utilization is significantly lower than its memory utilization. These utilization levels indicate that the performance of the kernel is most likely being limited by the memory system. For this kernel, the limiting factor in the memory system is the bandwidth of the device memory. So this is the same conclusion we came up with ourselves using the metrics, using the DRAM read throughput and DRAM write throughput. But we didn't have to, analyze it ourselves. The system has gone through, looked at the output, and seen that, yes, this is indeed the case. It gives you a nice graph. And if you remember, I said that the utilization was about 72% of peak. Here it looks a little bit higher than 72%, maybe 75%. I don't know quite what the difference is here. I suspect it might be something to do with the way ECC interacts with the reporting, and I didn't include ECC in this, maybe. But we can see we're about 75% of peak memory throughput, and that I'm quite happy with that as a kernel. Other things you could see, so you could see a very high compute bar, which would imply that we're bound by computations. We could see that instead of the device memory being limited, we were limited by the L2 bandwidth. We could see that we were limited by neither compute or memory, in which case we'd expect to be latency bound. But up here at the top, it will tell you what it believes to be the case. As I've said, if you know otherwise, then you're probably right. I mean, it's a computer. It's not necessarily going to analyze it correctly every time. If you as a human think that it's analyzing it wrong, you may well be right. But it will give you a lot of guidance as to what it thinks is wrong. Now, there's a lot of options. I could go deeper into the memory bandwidth analysis. I could look at the so that will let me see the L2 bandwidth. It will let me see the L1 bandwidth. It will let me see the total memory bandwidth. So there's a lot of detailed bandwidth information I can get from that. I can look at the compute analysis. So I can look at the load on each parts of the compute system. If, for example, I'm doing a lot of integer operations unexpectedly, then maybe I want to look at my indexing arithmetic or try to figure out where those integer operations are coming from so I can reduce them. And there's also latency analysis. So I spoke yesterday briefly about occupancy and needing enough blocks or enough threads on your streaming multiprocessor. The latency analysis will tell you how many you have and perhaps give you some thoughts or suggestions about how you could get more. It's more useful once you get a bit more experience with it. I mean, the guided parts are useful. The text, when you read through it, gives you some interesting information. However, as with all tools, once you get a bit of experience, figure out what's likely to be the problem, you can quickly narrow it down. You can do your latency analysis and say, oops, I'm accidentally using fewer threads per streaming multiprocessor than I thought I was, so I can make this quick tweak and suddenly it's going faster. So my profiling workflow is typically this. When looking at an application I've not seen before, or when tuning an application I have seen before, I usually go straight up and do nvprof./application. That's where I usually start. That will, well, firstly, if I think I've improved a kernel, that will tell me if I've improved the kernel. It will give me the average runtime of the kernel before my changes, and then I make my changes, compile, run it again, average runtime of the kernel after my changes. So I can say, oh, look, I've made it 20% faster. So that's a very quick way of getting the profiling information. I know it's very low overhead. The timeline's a good place to go next. So you will see some things that you don't need to know in this case. I don't need to know the memory bandwidth requirements of this particular kernel. I don't need to know the flop count of this particular kernel. I need to look at the timeline and say, wait a sec, I'm not actually using the GPU as much as I want to be using the GPU. So I have to then, the biggest optimization here is using the GPU more. I don't have to have the low-level information for that. So I would say that you should only really dig deep into a kernel if it's taking a significant amount of your time. Optimizing something that takes 1% of your runtime is just going to be a lot of effort for not much gain. Maybe if you're really desperate, if your application needs to be 1% faster, then it's useful. Only if it needs to be 1% faster, though. Or maybe you have a lot of kernels which are very similar, and each of them take 1%, and so you know a bit more than the tool, so you know that an improvement to this 1% kernel can then be rolled out across all your kernels. I like to, where possible, try to match the profile output with theory. So if I know I'm moving 1 gigabyte of memory from my device memory and back again, and my kernel takes 10 milliseconds, I expect the profiler to tell me I'm moving 100 gigabytes a second. If it does not, then either I have a bug in my application, or my expectation is wrong, or there's something I am doing within the application, so maybe I have some funny memory accesses which is causing a different amount of memory to be moved. Or, of course, the application may be compute bound rather than bandwidth bound. But knowing all of these things when you're optimizing a kernel is very useful, and checking that things are as you expect will often give you useful information if they are not as you expect. If something's not doing what you think it is, often it will be going slowly because it's not doing what you think it is, and that's something you can fix. So that was a quick rundown of our two profiling tools that you can access, the visual profiler and the command line profiler. Both should be available on your systems, and the third hands-on lab, one part of it is to look at the application you worked on in the second hands-on lab and look at it in the profiler and just have a play around with it. I'm now going to talk about data movement, optimizing data movement. So we've said that data movement is often a slow part of your application. It's something that takes some time. So what can we do to reduce this cost if we can't just remove the data movement? So here's our standard heterogeneous computing picture. We have our CPU on the left, our PCIe bus, which is slow, and then we have our GPU on the right. So we want to optimize the transfers over the PCI bus. So what are the costs of moving data? Before we start optimizing, first we have to sort of understand why is it slow. There are two main costs. So these are two main costs with most operations. There is both throughput and latency. In this case, bandwidth and latency. For a large copy, we are likely to be bound by bandwidth. We're going to be going at the peak bandwidth of the link, probably. For a small copy, however, we're likely to be limited by latency. So if we just want to copy 4 bytes from the CPU to the GPU, or vice versa, we're not going to be anywhere near the peak bandwidth of the connection. We're going to be bound by latency. So many small copies are significantly more expensive than one large copy of the same size. The peak PCIe bandwidth is 16 gigabytes a second. You won't see 16 gigabytes a second in reality. There's quite a bit of overhead on PCIe on the protocol. You'll be quite lucky to see 10 probably. So there's several optimization options when you're looking at data movement. I've broken it down to the 4 main ones. The first one is do less of it. We've already seen this. We've already seen that by moving our data clauses outside of our kernel in hands-on 2, that we're doing less data movement, and therefore we're going faster. So that's a bit obvious, but it's worth saying. It's the first thing you should be looking at. Are we moving too much data? The second thing is to improve the latency by fusing small copies into larger ones. So if I have, say, 100 4-byte copies, or let's say 1 million, let's go wild, let's say 1 million 4-byte copies, it may be worthwhile to have a subroutine to pack these into one copy, do the copy, and then a kernel to unpack them into 4-byte regions, if that's really what you need. It may not be. It's hit and miss. But copying a large contiguous area is going to be faster than copying lots of small areas. And if you do have a contiguous area, copy it contiguously. Don't break it up into lots of small areas and copy it. The third one is use pinned buffers. So there's 2 main ways of allocating memory on the CPU. There's page-locked or pinned memory, and there's pageable memory. Page-locked is able to be transferred directly to the GPU, whereas pageable memory has to be moved into a page-locked region before copied, or not always, but it is slower to transfer to the GPU, I suppose, is the main point. So using page-locked buffers will increase your bandwidth and probably reduce your latency. And finally, overlapping data movement with execution. The GPU is capable of copying data to and from the GPU at the same time as executing a kernel. Different GPUs act slightly differently. Some have 2 copy engines, some have 1 copy engine. The ones with 2 copy engines can copy data to the GPU from the GPU and execute a kernel all at the same time. The ones with 1 copy engine can only copy to or from and execute a kernel at the same time. You can't copy both to and from at the same time if you've only got 1 copy engine. And I'd like to say, as soon as I start talking about optimization, I always say profile first. I've just talked about profiling, but profile before optimizing. Don't spend all your time optimizing something that isn't significant. In a lot of cases, data movement is not a significant performance hit. In a lot of cases, it's not worth going to the effort, maybe making your code more complicated, to optimize data movement, because it's only taking 1% of your overall runtime.
Coming back to the pin buffers, if pin buffers are faster, why not use them all the time?
Because if you have too many pin buffers on your CPU, your operating system doesn't like it so much and starts to go a bit slower. So pageable memory is much more convenient for the CPU and the operating system in terms of running nicely. The overall pinned memory space you have is significantly less than the pageable memory space, for example.
So the recipe is to pin the memory that is more sensitive to these issues of data movement. Try to leave the rest unpinned.
Yeah, well, you can experiment. So in some cases, pinning everything is the right strategy. In some cases, it's not. So it's your mileage may vary. So I'm going to go through each of those points in a bit more detail. So how can we do less data movement? Well, the most obvious one is moving the data movement outside of the main loop. So an iterative solver doesn't want to do data movement within the iteration loop. You want to do it outside of the iteration loop. Keep everything on the GPU as much as possible. Now, as you're porting an application to the GPU, or you often find that these memory copy stages are unavoidable. So if I have a million, well, let's go slightly less extreme than a million now, 100 subroutines within a time step. Until I have them all working on the GPU, I cannot avoid copying memory back to the CPU if I want to carry on getting the correct answer. So if you're doing intermediate performance analysis, before you've finished moving your entire time step loop onto the GPU, you're going to have these copies, and they're going to show up in the profile, and your application is going to go slower than once you have got the entire time step loop ported. If you're doing a performance study of an individual section of code, for example, you should probably neglect the cost of the memory copies, because in the final application, your particular case study will not have those copies. All the data will already be on the GPU at the start of the subroutine. So do be aware that if you're doing intermediate performance analysis, that you will have memory copies taking up time, which don't necessarily shouldn't necessarily figure in your analysis. One other tip is consider if data can be passed as an argument in CUDA or declared as private. So copying a 4-byte thing which could be passed as an argument into device memory and then reading it in a CUDA kernel is quite inefficient compared to just passing it as an argument. It's because of this latency, so you pay the latency for doing the memory copy, and that's unideal. This is why we used value in CUDA Fortran to prevent this extra copy. It sounds a bit flippant, do less data movement, but it is something you do have to think about a little bit. The second point I made was fuse small copies into large ones. So small copies are inefficient because of latency, because the PCIe bus actually works better when you have larger copies, bandwidth, latency aside. So if the opportunity arises, merging copies can be beneficial. It's not always possible, and the way to do it isn't always natural. So if we have a large stride on a particular piece of data, so if we had, for example, a 2D stencil code and we wanted to do a halo exchange of one of the sides, well, one of the sides is contiguous in memory and one of them is strided in memory. So what we could do is we could pack the strided section into one buffer, copy it, and then unpack it on the other side. And in some cases that's beneficial, in some cases it's not. It may depend on how you do the packing and the unpacking. So if you notice yourself doing a lot of small memory copies, it's something to consider, but as with a lot of optimizations, your mileage may vary.
Are there actual CUDA routines that more or less do that for you with sliced copies?
I don't think so. There may be. There certainly isn't available in OpenACC.
No, this would be actual CUDA.
Actual CUDA.
I think you can copy subarrays, slices of subarrays, well, slices of arrays, i.e. subarrays.
I'd have to check the documentation again, but
for 2D,
so yeah, but okay, yeah. There are, you have to allocate your memory in a special way to do that. You have to allocate it with malloc pitch.
Yes.
So that's not always possible. But yeah, no, that's something that can help it. But whether that mem copy is going to be faster than what you wrote yourself, as you know the application here, and having a fixed function in this case may not be the best way of doing it. I don't know. It's something that if it is a problem you need to experiment with. There's no one solution, and there rarely is one solution to optimization. Pin buffers, so also known as page lock buffers. They generally have higher bandwidth. They generally have lower latency, but can harm system performance if they're overused. I believe OpenACC implementations will do this automatically.
It's a fair question. So behind the scenes, the PGI implementation allocates pin buffers, and when it does data transfers, the mechanism is it uses the host to copy the user data to the pin buffer and then does an asynchronous transfer to the device. Inverse. When you see your profile, it looks like you're doing host async copies, even if you didn't use async, because the runtime is doing the async copy, the double buffer to overlap the host part with the device to host to device. And it works well enough, so we're happy with it.
So there's nothing you have to do particularly to get fast memory. Okay. In CUDA, there's two ways of doing it. You can either register a normal allocation to be page locked, or you can allocate a new region of page locked memory. In CUDA Fortran, there's an attribute similar to device, pinned, which tells the compiler to allocate this region in pinned memory. You can also probably call the CUDA API routines directly in CUDA Fortran. It's true of most CUDA routines in CUDA Fortran. As I said, it can harm system performances if overused. And you have a smaller amount of pinned memory than you do pageable memory. Finally, overlapping data movement with execution. So when you're using pageable memory, PCIe transfers can occur at the same time as kernel execution. In CUDA, this is CUDA memcopy async. In OpenACC, you use the async clause on parallel kernel directives. And in some cases, this can reduce the overhead of copying memory, or the cost of copying memory, nearly to zero. So if you have a kernel that takes 10 seconds and a memory copy that takes 1 second, you overlap them. The memory copy you just don't see. It happens in the background as the kernel is executing. There will be a small cost associated with it. It's impossible to get rid of it completely, but you will no longer see a whole 1 second of memory copying. So you will really increase the performance of your application. If you are having a problem with memory copies and you do find a way to overlap them, I would strongly recommend it. It is probably the most effective way of dealing with memory copies you can't get rid of, is to overlap them with kernel execution. So to summarize, there are good and bad ways of moving data between the GPU and CPU. For many applications, it just doesn't matter much. So I was finding with Nemo that I had some memory copies that they were, if you looked at the profile, they were everywhere, but they weren't particularly expensive compared to my computation. I could have spent a long time optimizing the memory copies, but I wouldn't have gained much application speed up. This is because in Nemo, the majority of the data sits on the GPU for the application's lifetime. Next generation GPU. So while I've said that many applications is not important, it is important for some applications. And this is one of the reasons where the next generation GPU is going to bring some hardware improvements into copying memory. This is called NVLink, and this is a much faster way of transferring memory to and from the GPU and between GPUs. I have a slide on it here. So it's a high-speed interconnect to either go alongside or replace a PCIe. I said that PCIe was 16 gigabytes a second. NVLink will be somewhere between 80 and 200 gigabytes a second. it's more energy efficient, and it's more flexible. So you can do quite a number of different ways of connecting GPUs and CPUs with NVLink. So that is coming in our next generation of GPU, Pascal, which I'll hopefully have time to talk about at the end of this presentation. But is really going to improve applications which spend a lot of time moving memory. It's an order of magnitude speed up on the memory transfer times.
But this doesn't really help between nodes.
Doesn't help between nodes. Yeah, so you can copy this GPU to CPU step will be faster. So it's a replacement for the PCIe link. It's not for the interconnect. Yeah. So I have some early numbers here. This is what a CPU might look like. So depending on the CPU, you can either connect NVLink to it or not. But you will certainly be able to connect GPUs together using NVLink. And here are some application speedups that we have. So Fluent, CFD package, gets about 1.25 times. Sorting is nearly 1.5 times. Quantum chromodynamics, I think CUDA is. I don't know how to say QUDA. Amber is molecular dynamics, and 3D FFT. That does a lot of communication, so it's really helped out by NVLink. These are performance within a node, I think. So using the GPU to GPU connection. I'm now going to talk about multi-GPU programming, or using MPI with GPUs. How can you communicate between GPUs with MPI? So I don't know how much everyone knows about MPI. MPI is a system which allows you to pass, it stands for Message Passing Interface. It allows you to pass messages or data between processes on your system, which is, it's a standard way of making applications work over a number of processes, over a number of nodes, up to tens of thousands, hundreds of thousands of processes. Our system with CUDA looks roughly like this. So this is a 1 GPU per node system. So we have a GPU connected to its memory, a CPU connected to its memory, each connected to a network card, and we have n nodes here. MPI can be used to speak directly from one GPU's memory to another GPU's memory. Obviously, it has to go via the network card and across the network and up to the other GPU's memory, but the key point is it doesn't have to visit the system memory. So the natural way of programming MPI with GPUs is simply to copy the data to the CPU and use whatever CPU MPI you were using and then copy the data back to the GPU. You don't have to do that. There are GPU-aware MPI implementations, and they're significantly faster than using the copy, MPI send, copy, MPI receive, copy back methodology. So what you essentially do is, instead of giving a CPU buffer to your MPI command, so if we're doing an MPI send, this first argument is the data we're sending, we just give a device pointer. So sbuff_d, the underscore d is just a label for the programmer to tell you that it's on a device. It's not compiled into anything, but that tells us or implies that the GPU data is being used in MPI. And some MPI implementations will support this. They will just allow you to pass a GPU buffer to MPI, and it will be transmitted directly from GPU to GPU without having to go via the system memory. Skipping out this intermediate step means it's quite a bit faster. So I have already quickly described what MPI is. It's a standard to exchange data between processes via messages. There's quite a large API. Point-to-point messages are MPI send, MPI receive. There's also collectives, so you can reduce or do a summation, for example, or a maximum using a reduction operator. You can do all reduce. You can do all-to-all communications, though they're generally to be avoided because they're quite slow. And I'm not going to cover everything MPI can do. It can do quite a lot. Barriers. There are multiple implementations, open source, commercial. There's bindings for C, C++, Fortran, Python, etc. Here's a list of some of the implementations which are available. Cray, OpenMPI, IBM, Intel. Intel's not on there, but Intel have an MPI implementation.
Yeah, but not all of them are capable of transferring data from GPU to GPU.
Not all of them are GPU aware, you're right. I will say which ones are in a couple of slides. Compiling and launching MPI, you have to use a special compiler. Sorry, it's a wrapper compiler. This is a C application I'm running here. MPI CC would replace GCC or PGCC or any your regular compile lines. So for Fortran it would be MPI F90, for example. And then we call MPI run with a number of processes we want, and then your application. Similar to nvprof, you just put MPI run in front. And then that spawns four versions of your application, each running on a separate system, a separate node in this case. Typically, you want to launch one MPI process per GPU. There are ways, advanced techniques involving launching multiple processes per GPU, but typically you want to launch one per GPU. And there are 4 CUDA-aware MPI implementations currently. There's NVA pitch, there's OpenMPI, which I think we'll be using in the hands-on. There's Cray, and there's IBM Platform MPI. OpenMPI has enabled by default NVA pitch, Cray, and IBM Platform MPI. You should set an environmental variable to 1 before trying to use CUDA-aware MPI. I don't know if the environmental variable is still needed for NVA pitch, actually, but it may be. I'd have to check. But it's available without any changes on OpenMPI. Where am I going with this? I think one thing that, let me just check. Yeah, so one thing that is needed for not sure this is strictly true. I'm just checking myself. Yes, it is. Okay, yeah. So one thing that's needed for MPI is a unified virtual address space. That's one address space for all CPU and GPU memory on a node, and you can determine where a pointer is from this address. You can determine whether it's on a GPU or a CPU, or the runtime can. And that allows CUDA-aware MPI to work. So it allows, when you pass a pointer to the MPI routine, it allows it to work out where that is, whether it's on the GPU or the CPU. And that's supported in all supported CUDA GPUs. It wasn't supported in the first generation, but they're no longer supported GPUs. 64-bit applications on Linux and Windows using TCC mode. So there's a special mode in Windows for if you're doing performance applications on it, which is not the default Windows install or default Windows mode. Most of you, I imagine, will be running on 64-bit Linux, so it's supported there. The difference between unified virtual addressing and not unified virtual addressing is that without unified virtual addressing, there are separate address spaces between the CPU and the GPU, so they can overlap. So I can pass, there's obviously one pointer can point to either the CPU or the GPU memory, I just don't know. Whereas with unified virtual addressing, there's a single address space, so we know where the pointer points to. So with unified virtual addressing CUDA-aware MPI, we just pass the buffer, the device pointer, or the device buffer to MPI send. Without it, we need to do these copies, as I explained earlier. We have to go by a naive route and copy to the CPU, do the send, do the receive, copy back to the GPU. It's a lot less efficient. We're on OpenACC. This would look like this. So to get a subroutine call to use the device buffer rather than the host buffer, because obviously in OpenACC you have a single variable with both device and host attributes. You have to use this ACC directive, host data use device, and this will tell MPI that to use the device pointer or the device memory of SBUF and RBUF. And on the right there, we're using update host and update device to do it all manually. On the with OpenMPI and the supported MPI implementations, you should be using this on the left. If you're using an unsupported MPI implementation, this one on the right is probably what you want to be going for. There are ways to optimize the one on the right. I'm not going to go into them because I think you probably, if you're using CUDA and MPI, should be using a supported MPI implementation if at all possible. This essentially allows us to go from GPU 1 memory to GPU 2 memory. Now, one other thing it allows us to do, this more recent support, is for connection straight to the InfiniBand card, straight to the network. If you have this support, then you can go straight to the network. If you didn't, then it would sort of bounce it through the CPU without really pipelining it. Well, while pipelining it, so without much cost. Again, this support for RDMA is quite widespread now, but is only really a performance thing. It doesn't change the way you program your application. It just makes it so that things are a little bit faster. And here's how much faster. So for large transfers, it doesn't matter a whole lot. For very small transfers, it doesn't matter a whole lot because you're latency bound. But for intermediate transfers, so between 256 and, what's that? That's 1 megabyte transfers. It's a bit faster than doing regular GPU or MPI. I should point out here that we've got regular MPI here as well. So regular MPI is our copy to host, send, copy back from host method. And that's about 3 times slower on this case. This is a 2-node case. And one thing to point out with GPU Direct RDMA is the latency. So I have the latencies down here. The latency improvement for using GPU or MPI isn't that great, 2 microseconds, but by using the RDMA, so it's a remote direct memory access, it's a bit faster. Now the RDMA requires a supported interconnect, so may or may not be available on a given platform. But if you have an option to run on the platform with it enabled, you will see that it does go faster than a platform without it enabled. So I have a few slides after this, so this isn't the end of the talk, but this is the end of what I was asked to talk about. I'm going to add a few slides on our next generation GPU Pascal after this. Were there any questions on the 3 things I've talked about?
Almost on what you talked about.
No, it's fine.
Just on the side, you mentioned starting MPI tasks with 1 task per GPU. In a situation where you have code which has a top-level MPI, but that's not so much the question that interests me, has an OpenMP high level and then uses OpenACC below. What do you have to do to try and make sure that each OpenMP thread has the optimal connection to a GPU?
So each OpenMP thread would ideally run on a separate GPU. So there are API calls, it's ACC set device, I think it is, in OpenACC, and CUDA set device in CUDA. You also have to worry a little bit about thread affinity. So ideally, your OpenMPI or your OpenMP thread should be on the same CPU as your GPU is attached to in a multi-CPU system, and they also shouldn't be. They should probably be pinned threads. So you then have to play around with your OpenMP implementations, environmental variables to try and get this to work, or maybe call some API functions to get this pinning correct.
That's a good question, and what you're really saying is we have no good solution.
Well, maybe. Yeah, there's not an ideal solution. There are bad solutions, I guess.
There are other messy solutions like
So I also said that you'd have one MPI rank per process. And this isn't the only way you can do it. You can have multiple MPI ranks per process.
Which will then share the GPU context.
They'll share it, and they will effectively run in separate streams on the GPU. However, this requires a bit of an intermediate step, which is called MPS, so multi-process service. So you need to run a daemon to combine the launches from the two streams into one. And that will tend to add a little bit of overhead, mostly launch latency, onto your kernels. In general, you don't need to use MPS can be a good way of taking a partially ported application, something that doesn't use the GPU much, and getting it performant. So getting the most utilization out of your GPU. But in general, you want your single thread to be using the GPU as much as possible. That's always going to be the fastest way of doing it.
And this MPS step is something which happens automatically with OpenMP and OpenACC?
Does not happen with OpenMP, does with MPI. So it's processes, not threads.
For example, to start with a system, it's more than pretty easy to have a node, to be working on a node that has more threads, more cores than GPUs. What
Trivially easy, I think. Any system you're on.
So
You're not spending your money wisely.
that's another question.
with OpenMP,
What is the recommended
well,
case for something like that in Fortran with OpenMP and OpenACC?
you typically have one core per GPU. You can launch work to a GPU from multiple CPU threads into different streams. And that is actually more efficient than MPS. So that is a route that doesn't work. It can help you avoid redesigning your application, though redesigning your application will probably result in faster overall code.
You say it works, but I'm not totally convinced. There are some constraints there, aren't there?
Oh, okay.
If you're using normal MPI and you're using, say, 1 rank per core, and you have, say, 2 or 4 GPUs, there's not enough GPUs, and you want them all to be using a GPU, they're going to be sharing, you can use modules to figure out which GPU to use. You're going to share the GPU. Normally, I don't know how MPS works, I'll be perfectly honest, so that's...
It intercepts the calls from your process and binds them into one process. So if you have multiple processes, it's not.
I still don't know quite how that works with respect to the OpenACC runtime. The OpenACC, we've made this work with MPI and sharing GPUs. They're separate processes, though. They each have their own they each have their own CUDA context, and they have their own host address space. They don't share context, they don't share data on the device. You can run out of memory on the device because, you have to manage your memory in a way, because when it fails, it's not light.
One of the features of MPS is that all of the CUDA tasks are in one context.
Is that true with OpenACC as well?
I think so, but I've not tried MPS myself with OpenACC. So. Yeah.
I don't know how that works. With OpenMP, the way it's supposed to work is, and we made it work, is with OpenMP, if they're using different GPUs, and each thread that has a different GPU will have its context, they'll have a different context, one for each GPU, and they'll have the data on each different GPUs. And you can have data replicated across GPUs, and then you've got coherence problem, right? Host, GPU, and GPU, and where's the current update? Who's managing the coherence problem? Okay, so that's an issue. But if you have more OpenMP threads and they're now sharing a GPU, the way it's supposed to work is you get one context that's shared across all the threads. Shared data on the host will be shared data on the device. Now, what I have learned, and this came up in the hackathon in Lugano and came up again compiler that you guys have installed here. There's a race condition in data management. And so with multiple threads, it only, in Lugano it only happened when we got up over 15 threads, but here it happens with 2, so your system is particularly challenging. So that the present table doesn't work all the time. It's basically broken. So I would not try to use OpenACC inside OpenMP sharing a GPU with 1570.
Works with CUDA though. It doesn't, yeah.
Mike, it just killed my presentation because I can use it.
Yeah.
I mean, I ran into race conditions around 12 threads.
Yeah, well, I ran into it in 2 threads, so it's hideously embarrassing.
But is it fixed in 15.9?
I have to test it because I never ran into it with 2
Okay.
threads, so I'm going to test it when I get back home. It will be fixed in 59. How's that? We won't release it until it's fixed. This is just a perfect example why parallel programming is really hard. Even guys who think they know what they're doing, obviously don't.
Well, it's attractive to have multiple threads somehow active on a GPU in terms of
Well, you saw his profile, right? There's
Yeah.
always blank space in the
Yeah,
GPU,
exactly.
so you get 2 threads, you're filling in the blank space.
Yeah.
You're using a resource as much as possible. And if you can do that, then it seems attractive.
What happens if you do a device synchronize? Does it mean that everybody across all threads are held up at that point?
Yeah, that will block the entire GPU. So what you then have to do is, you use streams. Yeah.
Well, Kublas.
For instance.
Yeah.
Is there any, I can't remember my OpenACC format, is there any syntax for specifying I'll avoid saying gang because that would be a group of threads which have access, which control the GPU path, and another group which will continue on CPU.
Okay, so the issue he's running into, which is related to, basically it's saying, here I've got my parallel loop or what have you, and this thread I want to run, send it over to a GPU, these threads I want to run it on the host, in parallel, and maybe this thread run it on that GPU. So it's kind of if you think of the host as a device, it's selecting which device am I going to run this on. And there's no trivial way to do that. And the real problem isn't where do I run it, it's getting the data in the right place. And that's a challenge. You guys are all Fortran programmers, and some of you have heard of high-performance Fortran. And one of the issues with high-performance Fortran was distributing the data across the different nodes. Well, this is exactly that problem, distributing the data across your GPUs and your host and making sure the computation happens in the right place. And obviously, HBF couldn't solve it. So we're back to the same. It's a challenge, an opportunity. There's research papers to be written.
So I think it has been done by one of the guys in the US, hasn't it? But not necessarily with OpenACC.
So, yeah, there's a lot of interesting potential solutions.
Oh,
One
okay,
of the ones
potential. Right.
that I just saw recently was they're using runtime scheduling. So they try to do basically tasks. They launch a lot of tasks. Each task describes what data it uses, and then it schedules it where the data is now, and that someone else could steal it and has to steal the data. And, it sounds like it can work great, and they've got stunt mode cases where it works really great, and other cases where it works okay, and maybe that's the right thing to do. If locality works, then eventually everything will settle down and run really fast.
There has to be clear understanding, it's all ignored there, isn't it, totally. You don't see any mention of what happens if you use OpenMP and OpenACC. I think there should be a
There are some statements in there about using multiple threads, but OpenMP is not mentioned. And it's a fair point.
So any other questions?